For polynomials, so far we've only looked at the end behavior. We haven't really seen what happens to our graph when our x values are close to the point 0, 0. It turns out the degree of our polynomial directly relates to the number of zeros of our polynomial, and this in turn tells us the number of possible max and min values our polynomial function can have. For polynomial functions, max and min points are called turning points. And a turning point is a point on the graph that changes from increasing to decreasing or decreasing to increasing. For example, in the picture on the left-hand side, if we go in and fill in our graph, this polynomial function has two turning points, one right here and one right here, where the graph on the left-hand side of this point is increasing, and then on the right-hand side it's decreasing, which makes this point a max turning point, and the other turning point we have on the left-hand side of our graph is decreasing, and then on the right-hand side it's increasing, which makes this point a minimal turning point. An important fact about turning points is they're bounded by the degree of the polynomial. So a polynomial of degree n has at most n x-intercepts and n-1 turning points. So this will pop up again in the next section, where we really focus on graphing polynomial functions. For now, we'll use it to find a bound on the possible x-intercepts and the possible number of turning points. Let's find the x and y-intercepts, and then the local behavior of the function f of x is equal to 2x cubed minus 6x squared minus 20x by finding the max number of turning points. First, let's find the x-intercepts. To do this, we set our function equal to 0. And the solutions to this polynomial equation will be our x-intercepts. So pull out an x from the right-hand side, and we'll get 0 is equal to x times 2x squared minus 6x minus 20. Furthermore, we can pull a 2 out, and we'll get 0 is equal to 2x times x squared minus 3x minus 10. Factoring this equation, we'll get 0 is equal to 2x times x minus 5 times x plus 2. Setting these equal to 0, we see 0 is equal to 2x, 0 is equal to x minus 5, or 0 is equal to an x plus 2. Therefore, our solutions are either x is equal to 0, x is equal to 5, or x is equal to negative 2. So we'll have x-intercepts at the point 0, 0, at the point 5, 0, and also at the point negative 2, 0. Now, to find our y-intercept, plug in x for 0, then we'll get y is equal to 2 times 0, minus 6 times 0, minus 20 times 0, which means y is equal to 0, and we'll have a y-intercept at the point 0, 0. Now, in the last part of the problem, we want to find the turning points, specifically the max number of turning points. And to do that, we need to find the degree of our polynomial. The leading term is given by 2x cubed, which means the degree of our polynomial is 3. Therefore, by the previous important statement, we know the max number of turning points is 2. In this final problem, we want to determine the least possible degree of a given function, then find the number of turning points. In this problem, we're given a graph, and we see that the end behavior of our graph, as x approaches positive infinity, f of x is approaching infinity. And as f of x is approaching negative infinity, or excuse me, as x approaches negative infinity, our f of x is going off to negative infinity. So we know from this that the degree of our function is odd. Since we're given our graph, we can just see the number of turning points. We have a turning point here, we have a turning point here, one here, and one down here. So we have 4 turning points, which means the smallest possible degree our function can have would be 5. And in part 1, we already found the number of turning points. The number of turning points is 4.